Yeah, just making sure my microphone is on. Alright, so this is me, sleep deprived, but I have to do what I have to do. So I'm going to start this, the review process. Now, the reason I'm doing this is because I know some of y'all are stressed and time is limited and y'all have access to media. Anyways, you know the deal. Y'all are a technological generation, far more than mine ever was or will be. So here goes. Now, mechanics. I will attempt to summarize this entire section of the syllabus in 20 minutes or less. So mechanics has a few important things. The first thing is Galileo. Galileo. I hope I spelled his name right, but anyways. He not discovered, that's such a bad thing to say, but poorly put rather. He gave us the scientific method. And also, he kind of gave us the simple pendulum. And the simple pendulum. Now, moving on from Galileo. By the way, the scientific method should have been explained by your teachers, but doing labs, but let me explain it to you. The scientific method is a method by which it's basically how you go about doing a practical. You observe, you come up with a theory, you test your theory or your hypothesis, and you test it so that you can gather data, right? GATHER, data. Then you analyze this data, and you come to a conclusion. Now, if your conclusion proves your theory correct, full marks. If it does not, you have to backtrack to your theory and come up with a new one. Anyways, Galileo is swiftly followed by density. Density is equal to mass upon volume. Mass over volume. Relative density is density of a substance over density of water. Why did I put S? It should be W. Now, after this, after density, we move on to one of the most key or fundamental concepts in all of physics, and that, my friends, is the concept of force. So, force. Force is defined as any action which can change. Wrong place to put a comma. The size, shape, or motion of a body. Okay, this is force. Now, one of the forces that you have to look at is weight, W-E-I-G-H-T. And by definition, weight is the force produced when gravity acts on mass. Oh my goodness, my spelling is horrible. Now there's a formula for weight which you should be familiar with at this point. W is equal to M times G. M of course is mass, and G is the acceleration due to gravity. Now, the unit of force, in case you forgot, is the good old Newton, which we shall come to a bit later. But for the moment, we press on. We have to look at the effects of forces, EFFECTS, forces. The effects of forces, the first one we look at is deformation. Now, deformation is when force changes the size or shape of an object. That basically is what deformation is. Changing of physical dimensions by force, or by the application. That may sound scientific. Good. Now, deformation can be one of two types. It can be temporary or permanent. Temporary deformation is what we call elastic. E-L-A-S-T-I-C. And this is governed by Hooke's law. H-O-O-K-E'(S), Hooke's law. Then on the other hand, we have the complete opposite of temporary, which is permanent. Permanent deformation. By the way, I'm doing this at 5 in the morning. And this is plastic deformation. P-L-A-S-T-I-C, deformation. And we do not look at this, but just giving you some general knowledge. Now, temporary deformation, as governed by Hooke's law. Temporary deformation is temporary. I know, shocking, brilliant, and now, if you have an object, let's say this is your object, and you apply some force, and you stretch it, because you have applied this force, pulling the object that way, force. If you now remove these forces, the object should revert to its original dimensions. That is temporary deformation. And Hooke's law says the applied force is proportional to the extension obtained up to the fancy term limit of proportionality. This is Hooke's law. What does that mean? Well, in very simple terms, if we plotted a graph, right? Oh my days, me and straight lines. Okay, force, extension. The graph would be a straight line up to a certain point. That's basically it. The point at which the graph stops being a straight line is the limit of proportionality. That. Now the limit of proportionality is followed by the elastic limit. E-L-A-S-T-I-C-L-I-M-I-T. Now, the elastic limit, as the name might suggest, is the point. Yeah, this is a cheap definition. The limit of elastic behavior. E-E-H-A-V-I-O-U-R. The limit of elastic behavior. Now, I plotted a graph and I introduced force and extension. You might be wondering, why is Sir so cruel? Well, I'm terrible, I know. Hooke's law has an equation. Well, it has an expression. Force is proportional to extension. But we take this a bit further and we say F is equal to Kx. Give you 3 guesses as to what these terms mean. Of course, F is force. X is extension. And K is the spring spring constant. Now, please note, extension doesn't have a fixed unit. You might be like, sir, distance is measured in meters. True, but extension doesn't have a fixed unit because depending on the dimension of the spring, there are industrial springs that are a meter long, and the extension can therefore be measured in meters. There are those teeny tiny springs in your pen that are a few centimeters long, and therefore it would be better to measure the extension of such a spring in centimeters or millimeters. Extension kind of depends on the situation. Please note. Now, this is Hooke's law. Moving swiftly along, we come to the next thing. The next main topic is turning effect, Turning effect, or moment of a force. So, if we have, for example, let's say we're looking down on a door, yes, we're looking down on a door from above. I've over-exaggerated the hinge. That's the hinge. This is the door. Hinge, door. D-O-O-R. If you apply a force, F, on the door at this point, the door will tend to rotate in this direction. The turning effect or moment of force is the product of the magnitude of the force, the size of the force, and the distance the force is from the pivot. So the formula for turning effect is T is equal to F by D. T is turning effect. That's a horrible arrow. T is turning effect. F, force of course, in newtons. D is their perpendicular distance from the pivot. Distance of, I'm being fancy, point of application, APPLICATION, from pivot, PIVOT, in meters, and T is of course turning effect. This leads us to the principle of moments. Now you might be wondering, sir, how did we get here so fast? Well, I am not giving you examples. This is meant to be a short video just to help you with revision. Practice is, well, a different story altogether. So, let's assume we have a seesaw. Our glorious seesaw is sat upon by 2 individuals. Now, individual 1 produces a downward force of F1. Individual 2, this is a typical question, is now asked to sit somewhere to balance this seesaw. This is a typical principle of moments question. Now, the 2 individuals don't have to have the same weight, right? They don't need to have the same weight. They simply need to produce the same turning effect or moment of a force. Yes, I should stitch that in. Moment of force. Good. Meaning the moment produced by F2 should be equal to the moment produced by F1. Right? That's it. That's literally it. So, the principle, the principle of moments governs scenarios where we have forces producing several moments and the system is supposed to be balanced. And the principle of moments simply says that the sum of our clockwise moments should be equal to the sum of our anti-clockwise moments about the same pivot. Meaning, if you take the first moment about the pivot and the pivot is here, you can't then shift the pivot down here and then find a new moment. No. You can't do that. The pivot has to be in one place when both clockwise and anti-clockwise moments are calculated. And that is the principle of moments. You see how gloriously quick I am? Yes. I nearly quoted Kanye West when I was about to say bow in the presence of greatness, but this is no time for ye. Now moving on, we come to Newton, and we come to a straight line motion. STRAIGHTLINEMOTION. Straight line motion. Okay. This is going to sound silly, but we're only talking about straight line. We ain't talking about circle, we ain't talking about curve, we ain't talking about arc, we ain't talking about spiral, just straight line. So, a couple things need to be defined. If I'm moving on a straight line from point A to point B, my distance is going to be the same as my displacement. You might be like, sir, what do you mean? Distance, again, this is only on a straight line. Let me write that down. Only on straight line. Please notice straight line and not saint line. I know some of y'all might be a little confused. Numerically, the number, the size, the magnitude, distance is equal to displacement. This brings me to something I skipped that I now remember. I'm doing this off the top of my head without looking at the syllabus, so if I skip something or it's in slightly wrong place, forgive me. The idea of vectors and scalars. Now a vector is a quantity that has both magnitude and direction. Displacement is a vector, V-E-C-T-O-R. This is a scalar. Alright? Two objects can be 10 meters apart. That is their distance. Their displacement is more like a bearing. We could say B is 10 meters to the northeast of A. That is the difference between a vector and a scalar. A vector has direction and magnitude. A scalar has only magnitude. So there we go. The next quantities we need to look at be speed and velocity. Speed is roughly distance over time. And just like distance, speed is scalar. Velocity is displacement over time. How far you've moved in a given direction in what time. And just like displacement, velocity, I pointed to displacement, my bad. Velocity is a vector as well. This brings us to our final quantity, acceleration. ACCELERATION. Acceleration is equal to change in velocity over time taken. Change in velocity over time taken. So this is final velocity, meaning the velocity you end up at. This is initial or starting velocity, INITIL, and this is time taken for the change to occur. This is acceleration. These are the 5 terms that you may encounter, most likely will encounter, when looking at straight line motion. Now do remember, numerically, distance and displacement can be interchanged. Numerically, speed and velocity can be interchanged. But nothing can be interchanged with acceleration. Alright? Nothing. And again, only on a straight line. So moving on to velocity and displacement time graphs. Let us start with the displacement di, or distance or displacement time graph. Distance, time. I think you should do this for math. Y'all should do this for maths. Should. So let us assume we have an object, or we have a graph rather, and the graph is like this. Now, because your graphs are under what we call your graphs are all for uniform motion, where a constant force is applied, you're going to get straight lines. You're not going to get any curves. So basically what that means is your graph could only have like 3 different types of slope. Literally, just 3. You could have an upslope, we're going upwards. You could have a no slope or flat slope, and then you could have a down slope. For a distance time graph, A implies you have a velocity. Well, I use distance, so I should actually say speed, S-P-E-E-D, and you are moving away, A-W-A-Y, from a fixed point. Why away? Because if you think about it, your displacement is increasing with time. Yes, just because I didn't label the axes, this is distance. I said displacement, I should have said distance, my bad. This is time. If you look at A as you travel, yes, as you travel along A in this direction, your distance is increasing over time. B, no speed, because the gradient is 0. There is no change in distance along this graph. None. Absolutely none. So, there you go. No change. No speed, and not moving away. That's not a W, that's some weird new letter, A-W-A-Y. And finally, C. C does imply speed. But if you look at C, your distance is decreasing with time. Now you are moving towards whatever fixed point you are referencing, right? Your fixed point essentially is the origin, and you measure all distances from that point. Now, if this was, I shouldn't say if this was, the reason a lot of times, people just use the displacement graph is because you really can't, well, I shouldn't say you really can't, you still can't, you can tell direction, but it is just that a displacement graph is, it uses a vector quantity, and therefore you're more, anyway, just forget it, forget what I just said, ignore that. Just remember this: displacement time or distance time graphs basically mean the same thing, so using one or the other gives you no distinct advantage. Anyways, that was just me talking too much. Moving on to the next type of graph is a velocity time graph. Velocity time. And this is the graph that gives you all the good stuff, all the nice little juicy bits of information that you need. Now, this is time, this is velocity, and again, you could only have 3 types of slope. A, B, C. A, you are accelerating, A-C-C-E-L-E-R-A-T-I-N-G. You are accelerating. and this is an upslope. B, you have constant, constant, constant velocity, no slope. The graph is horizontal. And C, well, C is decelerating, decelerating. You are on a down slope. This is your velocity time graph. Now the final trick that the velocity time graph has up its sleeve is that the area under the graph, squididdly diddly 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 dee, dum dum dum, area under graph is equal to distance, displacement, I can't say, displacement or distance traveled. And that's your velocity time graph. Alright. Now, Newton's laws. Newton had 3 laws. The first law has a long statement, but an object at rest, I can't believe I'm saying this, stays at rest, and an object in motion, motion, stays in motion. Remember when we defined force, we said a force is any action which can change the size, shape, or motion of a body. Basically, Newton is saying here that force is needed to cause and change motion, motion. Good. The second law. He simply said that acceleration is proportional to force, and acceleration is inversely proportional to mass, which we combine and put as F is equal to m times a. That's basically it. And finally, the one that sounds like a scripture: to every action there is an equal but opposite reaction. This is what Newton said. Now, I don't need to explain the second law, but I might need to stitch this in under the third law. Basically, what Newton is saying here is that forces act in pairs. If you apply a force will be applied on you. And I think this is where I will bring an end to the first video, because I still have to look at work energy, power, conservation of energy. Actually, no. Let me look at, I forgot someone. I forgot my friend Aristotle. You see, good old Aristotle said something. Aristotle. He said that velocity is proportional to force. How fast you move depended on how hard you were pushed or pulled. Now, Aristotle didn't take account for one simple scenario. What happens when F is equal to 0? What happens then? And this leads us to something called momentum. Momentum. And momentum simply is what keeps a body in motion even when or after the force which caused motion no longer acts. Alright, this is momentum. Now, if memory serves, this leads us to the principle of conservation of linear momentum. But before I go to that, there's a formula for momentum. Common P is equal to M times V. This is momentum. This is mass in kilograms. And this is velocity. This gives momentum one of the weirdest units in all of CSEC physics, the kilogram meter per second, kgms to the minus 1. Alright, now, the next thing, the principle of conservation of linear momentum. Principle of conservation of linear, L-I-N-E-A-R, momentum. This simply states vector sum of momentum before a collision is equal to vector sum of momentum after a collision, provided that kinetic energy is conserved. Alright? Provided that kinetic energy is conserved. Now, the use of the term vector simply means you take direction into consideration. That is all. And that is the end of this first video in what is going to be a series of videos. Have fun.